For almost half a century, a small spacecraft has been traveling through the darkness far beyond the familiar planets of our solar system. Its name is Voyager 2. Launched in 1977, the spacecraft was created during an era when computers were primitive compared with the technology we carry in our pockets today. Yet decades later, Voyager 2 remains one of humanity's greatest achievements in robotic exploration. Its original mission was focused on the outer planets. And what it discovered changed planetary science forever. Voyager 2 flew past Jupiter and studied enormous storms raging through its atmosphere. It traveled onward to Saturn, examining the planet's spectacular rings and moons. Then came Uranus, a world tilted dramatically on its side, followed by Neptune, where Voyager discovered an atmosphere dominated by powerful winds and enormous storms. The spacecraft revealed worlds that had previously been little more than distant points of light. It discovered moons, investigated magnetic fields, measured radiation, and returned images that transformed our understanding of the outer solar system. But after completing those encounters, Voyager 2 continued outward. Its destination was no longer another planet. It was interstellar space. Attached to the spacecraft is the famous Golden Record, a collection of sounds, images, music, and greetings intended as a symbolic representation of Earth. The record was never designed as a practical communication system for contacting aliens. It was a message of curiosity. A reminder that a civilization on one small planet had decided to send something into the unknown. Then, in 2018, Voyager 2 crossed the Heliopause, the boundary where the influence of the solar wind gives way to the interstellar environment. This was a historic achievement. For the first time, scientists had direct measurements from a spacecraft traveling beyond the heliosphere. The environment outside our solar system was not simply an empty void. Voyager's instruments detected changes in particles, plasma, and magnetic conditions as the spacecraft moved through the boundary region. Its plasma instrument provided information about the density of material surrounding the spacecraft, while its magnetometer measured the magnetic field. These measurements helped scientists investigate how the Sun's protective bubble interacts with the surrounding interstellar environment. And what they found was more complicated than a simple wall separating the solar system from space. The boundary is dynamic. Solar activity can influence the heliosphere, while material from interstellar space interacts with particles flowing outward from the Sun. Voyager 2 is therefore doing something no telescope on Earth can accomplish. It is directly sampling the environment outside the Sun's protective influence. But operating a spacecraft at such an enormous distance is an engineering challenge unlike almost anything else humans have attempted. The spacecraft is powered by radioisotope generators whose available energy decreases gradually over time. Engineers must carefully decide which instruments can remain active. Communication is also incredibly difficult. The radio signal reaching Earth is extraordinarily weak after traveling across billions of kilometers. Large antennas on Earth must listen carefully for the spacecraft's transmissions. Even sending a command to Voyager requires extensive planning. A spacecraft designed in the 1970s is now operating in an environment that its original engineers could never have physically visited. Occasionally, unusual readings or changes in instrument behavior can appear in the data. But an unusual measurement does not automatically mean Voyager has discovered something artificial or impossible. Scientists have to consider radiation, aging electronics, changing environmental conditions, and instrument limitations before drawing conclusions. That careful approach is what makes Voyager's real discoveries so valuable. The spacecraft does not need to encounter an alien civilization to make history. Its greatest achievement is already clear. Voyager 2 has carried humanity beyond the familiar planets and into a region where the space between stars can be measured directly. And its journey is far from finished. As long as the spacecraft can communicate, every measurement it sends back becomes another piece of information about the enormous environment surrounding our solar system. The next chapter of Voyager's story may not involve a spectacular image or mysterious signal. It may simply be another scientific measurement. But even that ordinary signal will represent something extraordinary. A machine launched in 1977 is still talking to Earth from the darkness between the stars. Voyager 2's journey is more than a story about an old spacecraft surviving for decades. It is also a continuing scientific experiment. Every measurement collected beyond the heliosphere helps researchers understand how our solar system interacts with the enormous galactic environment surrounding it. The Sun constantly releases a stream of charged particles called the solar wind. This flow travels outward and creates the heliosphere, an enormous region extending far beyond the orbit of the planets. Inside this bubble, the solar wind dominates the local environment. Outside it, Voyager encounters interstellar space. But the transition between these regions is not perfectly simple. The boundary changes with conditions surrounding the Sun and with the pressure of material outside the heliosphere. Voyager 2 has therefore provided scientists with a rare opportunity to study this interaction directly. Its measurements of plasma, particles, and magnetic fields have helped researchers understand the structure of the heliosphere and the environment beyond it. The spacecraft has also detected cosmic rays arriving from outside the solar system. These extremely energetic particles travel through the galaxy and can provide clues about violent processes occurring far beyond our immediate neighborhood. Understanding how the heliosphere affects these particles may also help scientists understand the kind of cosmic environment surrounding other stars. And this is where Voyager's legacy becomes even more important. The spacecraft is not only teaching us about our own solar system. It is helping researchers think about planetary systems throughout the galaxy. Every star has an environment influenced by its radiation, magnetic field, and stellar wind. Our Sun is just one example. By studying the edge of the heliosphere, scientists gain information that can eventually help them understand how other stars may interact with their planets. Voyager's enormous archive also has value beyond the original mission. Modern computers can process information far more efficiently than the systems available when Voyager was launched. Researchers can revisit older measurements using improved analytical techniques and compare them with newer observations from other spacecraft. Artificial intelligence and machine learning methods may also help scientists search large scientific datasets for patterns that are difficult to identify manually. That does not mean AI is uncovering secret alien messages hidden inside Voyager's transmissions. Instead, advanced computational tools can help researchers organize data, detect long-term trends, and investigate subtle changes. The spacecraft itself remains a remarkable example of engineering. Its computers were designed more than 40 years ago. Its instruments have endured radiation, extreme cold, enormous distances, and the gradual loss of available electrical power. Every additional year of operation is effectively a victory against aging. Eventually, Voyager 2 will no longer have enough power to operate its scientific instruments or communicate reliably with Earth. But when that day arrives, its scientific mission will not truly be over. The data already collected will remain available for researchers. The spacecraft's discoveries will continue appearing in textbooks and scientific studies. And future missions will build upon what Voyager taught us. New spacecraft will eventually travel farther and may carry instruments far more advanced than those aboard Voyager. They could measure the interstellar environment in greater detail and explore regions Voyager can never reach. But those missions will follow a path that Voyager helped open. There is also something deeply symbolic about the spacecraft's continuing journey. Voyager 2 carries the Golden Record, which contains sounds and images representing life and culture on Earth. It was never guaranteed that another civilization would ever find it. In fact, the probability may be extraordinarily small. But sending it was an expression of human curiosity. We built something capable of leaving Earth and then allowed it to travel into the unknown. That idea remains powerful. Voyager 2 has not confirmed alien technology. It has not discovered an artificial signal. It has not revealed a hidden civilization. The truth is more remarkable in a different way. It has demonstrated that human engineering can operate across an almost unimaginable distance and continue returning scientific information decades after launch. From Jupiter's storms to Neptune's winds, from mysterious moons to the boundary of the Heliosphere, Voyager 2 has transformed our understanding of the solar system. And now it is carrying that story beyond the planets. One day, the last signal will arrive. The spacecraft will become silent. But Voyager 2 will continue moving through interstellar space, long after its instruments stop working. Its journey will remain a reminder that exploration does not always require knowing what we will find. Sometimes, the greatest discoveries begin with a simple decision to go farther. And Voyager 2 went farther than almost anyone in 1977 could have imagined. Its mission proves that even a machine built with technology from another era can change the way humanity sees the universe. The spacecraft is still moving forward. And somewhere in the darkness between the stars, Voyager 2 continues its quiet journey into the unknown.